Welcome, good morning. Today we will see chapter number 4, that is modes of control. There are different modes of control such as on-off control, proportional control, derivative control, integral control and proportional plus integral plus derivative control. We will see one by one. Now syllabus: on-off control, proportional control, that is P control, integral control, that is I control, derivative control, that is D control, and proportional plus integral, that is P plus I, proportional plus derivative, that is P plus D, and proportional plus integral plus derivative controllers, no numerical treatment. Therefore this chapter is only theoretical chapter. Now first control is on-off control. Now on-off control, you are knowing, in our house or at our home many electrical appliances are there which works on the principle of on-off control. Tube light, fan, mixer, oven, all these examples are examples of on-off control. A controller is a device which, when introduced in feedback or forward path of system, controls the steady state and transient response as per requirements. Such device converts input to the controller to some other form of error than proportional to error, due to which steady state and transient response gets improved. On-off controller is one of the most common and simplest mode of controller. It has to control two positions of control element, that is either on or off. Hence this mode is also called as on-off controller mode. It is the cheapest controller and often used if its limitations are within the tolerance. This controller mode has two possible output states, namely 0% or 100%. Mathematically, this can be expressed as P is equal to 0%, that is EP, that is error, is less than 0. P is equal to 100%, that is EP greater than 0. Equation 1, where P is the controller output and EP is the error based on percentage of span. Thus, if the error rises above a certain critical value, the output changes from 0% to 100%, and if the error decreases below certain critical value, the output falls from 100% to 0%. For example, the room heater. Therefore our room heater is the example of on-off control. Many examples are there. Tube light is there, fan is there, refrigerator is there, electric oven is there. These are the examples of on-off controller. If the temperature drops below a set point, the heater is turned on, and if the temperature increases above the set point, the heater is turned off. In all implementations of on-off controller, there is an overlap as the error increases through 0 or decreases through 0. Same case is our refrigerator or fridge. If the temperature increases inside the fridge, at that time the compressor starts working, and if the temperature reaches the whatever desired temperature or set temperature, at that time compressor shuts down. Therefore, this is nothing but example of on-off controller. Now this is the diagram of on-off controller. On y-axis control output is there, on x-axis error is there, 0%, 100%, minus 5p, 0, delta 5p, on-off controller with deadband. Such an overlap creates a span of error in which there is no changes in the controller output. This span is called as neutral zone or dead zone or dead band. Therefore, this from this 0 to this minus 5p, this is known as, or this minus 5p to 0, this is known as dead band. Now next controller, that is proportional controller, that is P controller. The output of controller is simply proportional to the error ET. The relationship between error ET and controller output P is defined or determined by constant called as proportional gain constant, denoted as Kp. The output of the controller is a linear function of error ET. Thus, each value of error has a unique value of the controlled output. The range of the error which converts 0% to 100% controller output is called proportional band. Mathematically, proportional control mode is expressed as Pt is equal to Kp into Et plus P naught, where Kp is equal to proportional gain constant, P naught is equal to controller output with 0 error. Direct and reverse action is possible in the proportional control mode. The error may be positive or negative because error is R minus B and B can be less than or greater than R. Now this is the feedback element or this closed loop diagram. R is the input, this is the summing point, its signal is positive. Now this here minus another signal is coming at a summing point, that is minus B, therefore output from summing point is R minus B. It is fed to this controller Kp. R minus B is nothing but Et. Et is equal to R minus B. Again it is fed to the plant and an output is there. Again from the output, if that desired output is not there, therefore signal is taken off from this takeoff point and that is again taken off by the feedback element and that is fed to the summing point, that is nothing but minus B. Now integral controller. In this, the value of the controller output Pt is changed at a rate which is proportional to the actuating error signal Et. Mathematically, d dt of Pt is equal to Ki into Et, where Ki is a constant relating to error and rate. The constant Ki is also called as an integral constant. Integrating the above equation, actual controller output at any time t can be obtained as P is equal to Ki into integration of Et dt plus P of 0, where P of 0 is equal to, or P of 0 or P of output is equal to controller output when integral action starts, that is at t is equal to 0, that is at time t is equal to 0. The output signal from the controllers at any instant is the area under the actuating error signal curve up to that instant. Therefore, this is nothing but error signal. This is the controller output Pt versus time t. If the value of error is doubled, value of Pt varies twice as fast, that is rate of the controller output change also doubles. If the error is 0, the controller output is not changed. The control signal Pt can have non-zero value when the error signal Et is 0. This is because the output depends on history of error and not on the instantaneous value of error. The scale factor or constant Ki expresses the scaling between error and controlled output. Thus, a large value of Ki means that small error produces a large rate of change of Pt and vice versa. Therefore this is the graph. On y-axis d dt of pt is there, on x-axis error is there. K2, this is the region when K2 is less than K1, Ki is equal to K1 and K2 is equal to K1. Now next, derivative controller, that is D controller. The output of the controller depends on the time, rate of change of actual errors. Hence it is called as rate action mode or anticipatory action mode. Mathematically, Pt is equal to Kd into d dt of Pt plus P of output, where Kd is equal to derivative gain constant. It indicates by how much percentage the controller output must change for every percentage per second rate of the error. Generally, Kd is expressed in minutes. The important feature of this type of constant control mode is that for given rate of change of error signal, there is unique value of controller output. The advantage is that it responds to the rate of change of error and can produce the significant correlation before the magnitude of the error becomes too large. Following figure shows how derivative mode changes the controller output for the various rates of change of error. Therefore, this is the error on y-axis, this is the time on x-axis. Similarly, another graph is there, controller output, that is percent P of output, 50%, 100%, this is time t, for different errors for how the output changes. Therefore, we will stop here. In next lecture we will see proportional plus integral control, proportional plus derivative, and proportional plus integral plus derivative controller. Thank you.